Before July 1st, 2025, scientists believed they had a solid grasp on objects from beyond our solar system. We'd encountered two such intruders before, backed by robust predictive frameworks and tools equipped to unravel any puzzle the universe might throw our way. That all shifted when 3I Atlas showed up, shattering our certainty faster than frost under a blazing light. The deeper we delve into this enigma, the more baffling it becomes. It emits carbon dioxide at levels that defy logic given its dimensions. It sustains vapor halos stretching beyond the path of Earth's yearly journey around the Sun. It displays molecular traces that align with no known birthplace we can conceive. Every fresh data point compels us to rethink principles we once deemed unshakable. Even the planet's premier observatories are essentially conceding they've met their match in a mere sliver of frozen stone, no bigger than a modest town. What happens when our top-tier knowledge crumbles before something as straightforward as a comet? Stick with us as we unpack how this intruder could signal the greatest breakthrough of our era or evidence that cosmic riddles remain beyond our grasp. Part 1. The puzzle of why 3I Atlas defies explanation. On July 1st, 2025, exactly at 14 hours 37 minutes Universal Time, a shift rocked our view of the heavens. This wasn't unfolding in a far-off galaxy or the abstract world of research journals, but smack in the middle of our own stellar backyard. The Atlas Survey Station in Chile, an automated scope routinely hunting for risky space rocks, spotted an anomaly that had no business being there. It registered as little more than a hazy blotch amid the stars, a drifting speck. 5 astronomical units from the Sun. Yet in mere hours, trajectory computations unveiled a revelation that rippled across the field of astronomy. This outsider followed a hyperbolic path with an eccentricity well over 1. In orbital dynamics terms, it's not tethered, it's a one-way traveler, destined never to loop back through our system. They labeled it C225N1 Atlas. To experts tracking these stellar nomads, though, it earned the moniker 3I Atlas, the third verified interstellar body to visit our celestial patch. Its velocity alone hinted at the extraordinary, 130 km or 209. That's not merely swift by our planet's measure, it's the quickest solar system guessed on record. For context, picture a standard bullet in flight. Then amp that pace by 170 times. That's 3I Atlas hurtling along, carrying the impetus of an alien star's domain. But velocity, we'd learn, was just the gateway to its enigmas. Days after its detection, the Gemini North Observatory in Hawaii aimed its 8-meter reflector at this space drifter. The sight challenged everything we anticipated from such a wanderer. Encircling its unseen core lay a hazy, tight-knit envelope. A swirl of particles and fumes actively venting under the sun's influence. This wasn't a lifeless hunk of cosmic scrap. No, this entity pulsed with vitality, exhaling misty trails into the void as solar rays roused ancient ices that had lain dormant for eons in the frigid voids between stars. The realization hit researchers like an incoming bolide. This was a relic that had braved the galaxy's harsh expanse, shrugging off radiation lethal to any Earth life, weathering near absolute zero chills. But as soon as our star's glow reached it, sublimation kicked in, ices morphing straight to vapor, birthing an ethereal shroud in the emptiness. Yet what truly disturbed was how this behavior illuminated its root. 3I Atlas wasn't merely slicing across our solar system, it was navigating a razor-thin gap between planetary. It traces its path with remarkable accuracy. The nearest pass by Earth is set at 188 astronomical units, about 270 million kilometers away. Secure enough, certainly, but the alignment felt suspiciously ideal, almost tailored for scrutiny. NASA swiftly deployed its premier tools, including the Hubble Space Telescope, the James Webb Space Telescope, the Swift Observatory, and the Transiting Exoplanet Survey satellite. The European Space Agency orchestrated worldwide monitoring operations. This interloper wasn't merely one more comet to log in the records. It served as an envoy from a distant stellar realm, bearing molecular clues that might unveil the environment of a far-off planetary birthplace. Nevertheless, as the planet's top observatories focused on this intruder, a disconcerting trend surfaced. Each scan only spawned additional puzzles rather than solutions. The entity's actions didn't align with any known patterns of space flotsam. Its makeup challenged standard theories on comet makeup, and its arrival in our solar system, hurtling at such blistering speeds while staying operational, hinted at origins wholly foreign to our neighborhood's celestial setup. The researchers couldn't ignore the paradox. This relic hailed from light years beyond, a distance defying easy comprehension. Still, it would linger for months in the somewhat known bounds of our solar system. An extraterrestrial guest pausing long enough for examination, yet racing onward so swiftly that each chance to observe proved brief and invaluable. When July shifted into August and initial high-resolution photos started flowing in from our cutting-edge gear, a single truth stood out sharply. 3 Atlas had no intention of yielding its enigmas without a fight. In fact, the deeper our insights grew, the stranger it appeared. The scene was primed for urgent pursuit, a contest with the clock to decode this puzzling drifter before it vanished eternally into the void of space, hauling its riddles back to the voids among the stars. Part 2. Navigating our cosmic backyard. Envision the solar system as an immense mechanism where worlds trace steady routes across the expanse and epochs. Then, think of a projectile launched from a remote galaxy, slicing through this stellar apparatus at inconceivable velocity, slipping amid the cogs with flawless calculation. That projectile is 3I Atlas, and its route via our local space weaves a narrative of stellar synchronization that's nearly dramatic. The intruder's schedule resembles a deliberate sightseeing route through the core solar system, though scripted in the heavens eons prior to Earth's formation. Perihelion, its nearest solar encounter, is slated for October 29, 2025. Far from the safe remove typical of comets, it promises a fiery skim between Earth's and Mars's paths, some 130 million miles from the Sun, near sufficient for solar heat to vaporize primordial frosts, but distant enough to evade total obliteration. Yet, this is where the stellar ballet turns eerily meticulous, bordering on torment. While 3I Atlas nears the Sun most closely, our planet will sit precisely across from it relative to the Sun. For almost 2 months, spanning late September to early November, the guest will vanish amid solar brightness, undetectable by any ground or space-based scope. It feels like the cosmos plotted to conceal the pivotal phases of this star-spanning rendezvous. The viewing period narrates a saga of stellar exasperation. Experts possess about 3 months to collect intel before 3 Atlas slips behind the Sun. Following its reappearance in December, be 6 weeks more until it fades too dim and remote for useful analysis. Such a cutoff would unsettle even the boldest reporter. But here, the reporters probe an entity that won't return in any lifetime. Still, the path dangles intriguing possibilities. Prospects abound for anyone ready to expand their view beyond our planet. On October 3, 2025, 3 Atlas will zip by Mars at a mere 29 million kilometers away. That's nearer than the planet's own satellites get to it. For the array of automated probes circling the Crimson World, such as the Mars Reconnaissance Orbiter, equipped with its advanced high-resolution imager, this offers a rare opportunity to capture images of an extraterrestrial interloper from a foreign viewpoint. In the realm of astronomy, positioning is key, and this particular alignment serves as both a boon and a challenge. When 3 Atlas returns to our night skies come early December, it will appear in the hours before dawn within the constellation Virgo, gradually shifting toward Leo over the following weeks. Yet by that point, it will be hurtling from the Sun at speeds exceeding 150,000 mph, dimming progressively each evening as it ventures back into the vast cosmic expanse. For hobbyist stargazers eager to catch sight of this stellar outsider, the outlook remains discouraging. At peak luminosity, 3I Atlas will scarcely hit magnitude 11 or 12, detectable solely via telescopes and resembling little more than a dim, hazy dot amid countless others. Expect no dazzling display visible to the unaided eye, no sweeping tail arcing across the heavens like those of Comet Hale-Bopp or Neowise. This guest favors subtlety over spectacle. The dynamics of its path add yet another intriguing facet to the enigma. 3 Atlas isn't merely swift. Its trajectory defies expectations. The hyperbolic curve indicates an initial speed of about 25 kilometers compared to the local standard of rest. Such velocity enables it to break free, not only from our solar system, but possibly from the gravitational pull of our entire galactic locale. This isn't fresh ejecta from a close stellar nursery. Rather, it's an entity that has roamed the Milky Way for an exceedingly extended period. As 2026 transitions from spring into summer, 3I Atlas will undertake yet another notable flyby, approaching Jupiter in March. This remote rendezvous has already inspired suggestions to reroute NASA's Juno probe, presently encircling the massive planet, for a potential rendezvous. It's a bold concept demanding exacting calculations in orbital dynamics and impeccable synchronization, repurposing a probe meant to probe Jupiter's core into humankind's inaugural intimate brush with a verified interstellar traveler. Yet the most sobering element of this astral itinerary lies in what it discloses about our place in the cosmos. We're deploying gear valued in the billions, synchronizing efforts among various space organizations, and enlisting top experts in planetary studies, all to examine an entity that will linger in our neighborhood for under 2 years before vanishing eternally into the galactic void. The route of 3 Atlas across our solar system transcends mere motion. It embodies a sequence of possibilities and constraints, with portals of access opening and shutting in line with timeless principles of celestial motion. Each passing day draws us nearer to our last shot at unraveling the secrets of this galactic nomad. Part 3. Initial Observations. Hubble's View. When the Hubble Space Telescope first directed its unwavering gaze at 3 Atlas on July 21, 2025, the cosmos presented a riddle enveloped in celestial glow. The resulting picture from Hubble's electronic detectors felt both recognizable and profoundly otherworldly. A droplet-like envelope of particles and vapor radiating gently against the endless void, but featuring contours that defied conventional illustrations. The specifics unfold like verse composed in scientific notation. The core, the dense center of this star-hopping enigma, stayed indistinct, manifesting merely as a luminous speck nestled in its gaseous veil. However, Hubble's superior lenses enabled researchers to establish a maximum on its dimensions, at most 3 and 12 meters across, approximately 5-6 kilometers in width. To contextualize this, from that viewpoint, it's tinier than the average city on our planet. Still, this minuscule piece from a distant stellar realm produced a surrounding haze extending thousands of miles outward in all directions. And that's when the ordinary starts to turn bizarre. Hubble followed the comet's path amid the fixed stars, holding 3 Atlas steadily at the center of its observation frame. Consequently, the background stars show up as luminous trails streaking the photo, forming a ghostly setting that gives the impression of the comet speeding through a luminous corridor. This imaging method turns routine data collection into unintended artwork, highlighting the differing speeds that distinguish this interloper from the rest of our solar vicinity. The haze itself narrates a tale of heat dynamics unfolding across an immense cosmic expanse. As 3 Atlas drew nearer to the Sun, passing the 4 astronomical unit mark where water ice starts to vaporize vigorously, the core initiated the release of substances in a mechanism probably inactive for eons. The particles of dust freed from their frozen prison created an approximately round envelope around the core, though with a clear stretching directed opposite the Sun's position. This pattern wasn't haphazard, it was pure science at work. The push from solar rays and the pull of gravity molded the haze into its typical droplet form. However, the tail appeared unusual. For typical comets, the anti-sunward stream material propelled away by radiative forces stands out clearly and boldly. In 3I Atlas, this element was curiously faint, nearly concealed. Early examinations from Hubble indicated it might exist, but lacked solid proof. The positioning felt mismatched, as though we were observing the tail edge on, squeezing it into near obscurity. This uncertainty lingered until late August, when the Gemini South Observatory in Chile obtained profound exposures that unveiled what Hubble had merely suggested. There, a slender yet unmistakable anti-solar tail stretched outward from the Sun, like a delicate filament caught in the stellar breeze. Astronomers' telegram number 17363 confirmed it formally. 3 Atlas had the tail that models predicted, though it followed its unique guidelines for detectability. The rates of dust ejection offered yet another enigma. Hubble's data indicated that 3 different Atlas was losing matter at levels similar to those seen in inner solar system comets at equivalent solar distances under the Sun's influence. This could appear comforting signs of standard foreseeable conduct, save for a vital exception. This entity had roamed the voids between stars for ages, subjected to galactic rays that ought to have profoundly reshaped its outer composition. Nevertheless, it acted like a pristine comet on its inaugural trip into the Sun's inner domain. The sharpness of Hubble's captures, among the sharpest possible from space-based vantage, uncovered yet another facet of the enigma. Although the instrument could limit the core's dimensions and outline the haze's form, it failed to discern any details on the surface or its spin. The core stayed a mere dot, its mysteries shielded by the radiant curtain of its personal gaseous output. We were probing this newcomer amid the mist it generated, akin to inspecting a beacon's light source while immersed in its glow. Most captivatingly, Hubble's data suggested patterns inside the haze. The dust wasn't evenly dispersed. There were gentle shifts in luminosity and thickness, implying dynamic zones on the core's exterior. Beneath that cloak of gas and grains, particular spots were ejecting contents into the void, producing the configurations Hubble spotted. Yet, absent finer detail or diverse perspectives, those configurations stayed as enigmatic as forgotten scripts. The light measurements brought forth yet another revelation. 3 Atlas appeared more luminous than anticipated for something of its projected dimensions, implying either a bigger core than the limit suggested or a facade boasting exceptional brightness. Each option sparked inquiries into its makeup and beginnings. Opaque, carbon-laden substances would yield a dim body. Gleaming frozen exteriors could account for the glow that Hubble detected. However, the array of potential explanations allowed far too much conjecture. As the month of August advanced and 3 Atlas drew nearer to the Sun, Hubble's monitoring recorded the lively changes in the coma. The hazy veil of particles was swelling, spreading out under stronger solar warmth. Still, the core stayed indistinct, an enigmatic lure from the cosmos that disclosed merely sufficient details to affirm its oddity while withholding clues to its essence. Before long, these visuals would merge with inputs from additional tools, each contributing fragments to an enigma that appeared increasingly intricate with each fresh look. Yet Hubble had laid the groundwork for visual assessment. This wasn't your typical fragment of cosmic wanderer. It was an entity calling for answers, one that tested our grasp of an extrasolar guest's appearance. Amid the soft void of the cosmos, 3 Atlas pressed on with its timeless voyage, now bathed in our star's radiance and examined by humankind's top-tier devices. Despite our advanced capabilities, the intruder stayed largely inscrutable, an enigma cloaked in celestial glow and enveloped in its own radiant haze. Part 4. The Chemistry Surprise. The cosmos possesses a knack for humbling stargazers, and 3 Atlas was set to offer a lesson in stellar modesty when the James Webb Space Telescope, our era's premier infrared observer, initially examined the intruder's light profile on August 6, 2025. The findings demolished all preconceptions formed from prior interstellar studies. The figures narrated a tale that defied logic. Carbon dioxide to water ratio 8.1:8.1. To grasp the remarkable nature of this finding, note that typical comets within our system exhibit the reverse trend. Water prevails in their composition by margins of 10 to 100. Even the driest known comets seldom surpass carbon dioxide to water proportions of 2.1. Nevertheless, 3 Atlas displayed a molecular profile so outlier that it stood alone in its class. Yet Webb's revelation served merely as the prelude. From August 8th through 12th, the PHEX mission, NASA's broad-spectrum infrared explorer, focused on this cosmic anomaly and revealed an aspect that upended all conventional comet theories. The carbon dioxide release wasn't limited to a tight zone near the core. Rather, it stretched out over no less than 348,000 km, close to 250,000 miles, forming the most extensive carbon dioxide coma documented for any comet. Picture the full Earth-Moon setup, then extend that span by half again. Such is the magnitude of 3I Atlas's carbon dioxide sheath, a spectral orb of vapor vast enough to engulf several planetary paths. The immense scope of this release area hinted at mechanisms at work on proportions that questioned our knowledge of comet dynamics. The spectral readings sketched a scene of radical chemistry. Although Webb identified strong carbon dioxide emission bands, the water signal came across as oddly subdued, so weak that certain experts doubted if 3I Atlas held any substantial water frost whatsoever. This clashed sharply with previous insights from the Swift Observatory, which had spotted hydroxyl radicals usually signaling water breakdown by light. At some point in the shift from solid ice to vapor to hydroxyl, the water account was fading away. SphereX introduced yet another layer to the molecular tale. Its expansive spectral survey uncovered absorption lines at 1,5 and 2,1 micrometers, spectroscopic markers matching water ice across the exterior or within the uppermost layers. Thus, the ice existed in a frozen state, yet an unknown factor was hindering its effective transition from solid to vapor. The exterior concealed mysteries that spectral analysis merely suggested. The difference from earlier interstellar travelers was remarkable. 2I Borisov, identified in 2019, displayed higher levels of carbon monoxide rather than carbon dioxide compared to water. This molecular indicator pointed to origins in a frigid outer disk setting where carbon monoxide ice could solidify. In contrast, carbon dioxide narrates a separate tale. It arises at moderate temperatures in areas where water exists as liquid or gas. Still, carbon dioxide might crystallize directly from the gaseous state. These findings sent waves through concepts of planet formation. Should 3 Atlas have originated close to a carbon dioxide snowline in a distant stellar system, it could embody substances from a belt-like zone similar to our solar system's asteroid region, too heated for water ice to persist, yet sufficiently chilly for carbon dioxide to form. Such conditions may abound near other suns, though we'd never examined samples from them previously. The widespread carbon dioxide envelope sparked deeper inquiries. How could a core, merely a handful of kilometers wide, produce and maintain a dispersing zone bigger than typical planetary paths? The underlying physics required either an extraordinarily dynamic exterior, surpassing the activity of any solar system comet observed, or an entirely novel process for expelling gases into the void. Some experts theorized that 3I Atlas was breaking apart, liberating carbon dioxide-laden fragments that kept sublimating as they drifted from the primary body. Alternatives posited that solar wind engaging with an existing gas halo might enlarge the visible extent of the emitting area. Each idea pushed the limits of established comet studies. The revelations arrived at a peak of intrigue. Right as 3I Atlas neared the prime observation period prior to solar alignment, its composition emerged as wholly distinct from our roster of interstellar bodies. We observed a singular chemical workshop in transit, fueled by our star, yet bearing the iced chronicle of a foreign planetary realm. However, the prevalence of carbon dioxide also implied a stark reality. If this mirrors standard interstellar matter, our frameworks for planetary development and change may overlook vital elements. The varied chemistry of 3I Atlas, alongside the differing profiles of 1I Oumuamua and 2I Borisov, indicated that the galaxy contains a diverse array of expelled remnants exceeding our theoretical expectations. As August yielded to September and the viewing opportunity started to close, scientists held datasets that were both groundbreaking and frustratingly limited. The makeup of 3 Atlas stood out as exceptional. Yet, did it signal a fresh category of interstellar entity or merely an outlier within familiar principles? That debate lingered unresolved. The cosmos appeared intent on sustaining suspense right to the end. Part 5. What we still don't know. 3 months post-detection, despite deploying humanity's premier tools on 3 Atlas, we occupy an odd spot, grasping fragments of vast unknowns. Every examination uncovers fresh aspects of this cosmic puzzle. Still, the core issues that count elude clear resolution. The core's dimensions capture this dilemma spot on. Hubble observations limit its width to between 320 meters and 6 kilometers a span, covering anything from a sizable structure to a modest town. This gap stems not from equipment shortcomings, but from probing a faint, indistinct target, veiled surrounded by its distinctive glowing envelope. The core might consist of a dense, luminous orb, or a stretched, shadowy mass flipping end over end across the cosmos. Lacking high-resolution images, our assessments are little more than educated speculations. The object's spin remains just as enigmatic. Typically, minor objects in our solar system rotate on timescales of mere hours, with their shifting profiles producing noticeable fluctuations in light as they rotate. Yet 3 Atlas has displayed annoyingly consistent luminosity, lacking any rhythmic changes that could disclose its rotational speed or axis. It could be turning at an exceptionally leisurely pace, aligning almost pole-on as seen from Earth, or boasting an exceptionally even terrain. Every option hints at distinct insights into its beginnings and makeup. The debate over water has turned into a near-theatrical saga in scientific circles. Initial scans from the Swift Observatory's UV and visible light instrument spotted hydroxyl radicals, which usually signal water molecules fragmenting under the sun's UV rays. The detection of OH pointed to considerable water release, aligning with what we'd anticipate from comet-like behavior. However, follow-up surveys by SphereX revealed the water signature to be unexpectedly faint, imposing limits that clashed with Swift's findings. This leaves us wondering if the water exists but is masked by viewing conditions, or if we must rethink how hydroxyl forms in comet-like settings. The shape of the tail introduces further ambiguity. Observations from Gemini South in late August at last spotted an anti-solar tail, validating theoretical predictions. Its debris driven outward from the sun by radiative forces. Still, why the delay in spotting it plainly? Its faintness relative to standard comets implies either oversized particles that defy radiative pushback or an observation angle that flattens the tail's form to the point of obscurity. Each idea prompts deeper doubts about the essence of 3I Atlas. The rhythms of its activity offer maybe the most captivating puzzle. Hubble's photographs reveal an extension of the coma pointing sunward, with material seeming to stream toward the sun instead of receding. This odd setup initially baffled researchers until they grasped how sightlines can distort perceptions of 3D gas dynamics. The illusion of sun-directed motion could just reflect our vantage on an intricate 3D venting process. Alternatively, it might signal truly odd mechanisms for this interloper's material ejection. Enigmas in makeup go further than the prevalence of carbon dioxide. Although Webb and SphereX have charted the primary gaseous components, they've only begun to probe minor elements. Consider organics, sulfur-containing molecules, inert gases. Every minor ingredient might reveal details on its genesis, thermal history, cosmic ray impacts, and the chemistry of its home star system. Spotting them demands telescope slots that are dwindling fast. Arguably, the most aggravating gap is our failure to examine 3I Atlas near its closest solar approach. That's precisely when intensified sunlight ought to spark the biggest shifts in outbursts in chemistry. The period of solar occultation will blind us to the peak event as this guest swings by our sun at minimum distance. We'll catch only the consequences, akin to showing up to a show post-finale. The velocity of 3 Atlas intensifies all tracking difficulties. Earthly scopes have to slew at speeds straining their alignment tech. Orbital platforms grapple with timetabling as the quarry zips through the heavens. Plus, the steadily growing separation ensures each postponed session sharply worsens the clarity of spectral data. The motion dynamics weave their tale of ambiguity. though its extrasolar roots are solidly established. Undoubtedly, pinpointing the stellar origins of 3 Atlas demands exact details about its path. Such details are constrained by our short period of observation and the gravitational disturbances it encountered while traversing our solar system. The leading hypothesis points to its roots in the galaxy's thick disk, amid stars born when the universe was roughly half as old as it is now. Yet this remains an informed guess drawn from partial information. The fundamental issue of what powers 3 Atlas's behavior is still unresolved. Does it involve the vaporization of ices, akin to a standard comet? Might it be breaking apart due to heat-induced strain? Or perhaps it's carrying an electric charge, engaging with the solar wind in atypical manners. The widespread carbon dioxide envelope indicates processes on a level that basic vaporization theories fail to account for adequately. With the solar conjunction approaching, the growing ambiguities generate a strange scientific strain. We possess sufficient insight into 3I Atlas to acknowledge its remarkable qualities, yet insufficient to grasp the reasons behind its uniqueness. The return in December presents a last opportunity to unravel the enigma or accept that certain celestial enigmas are destined to stay concealed. It appears the universe has a special affinity for intruders that bring far more inquiries than resolutions. Part 6. Defining what qualifies as interstellar. The universe may not hand out travel documents, but were it to do so, 3 Atlas would hold papers from a distant stellar realm. Grasping the essence of a genuinely interstellar body involves exploring the calculations of orbital dynamics, a dialect in which eccentricity figures and hyperbolic paths narrate tales of vast cosmic journeys lasting millions of years. In the exact jargon of celestial mechanics, any body exhibiting an orbital eccentricity exceeding 1 is not tethered to our solar system. It pursues what experts term a hyperbolic orbit, a route that expands toward endlessness instead of forming a closed oval. 3 Atlas boasts an eccentricity of about 1.7, signifying not only its freedom from binding, but also a speed so immense that Jupiter's formidable pull scarcely alters its course. However, eccentricity by itself doesn't reveal the full picture. The key indicator is known as V infinity, the speed a body would maintain with respect to the Sun at an infinite distance, free from solar gravitational effects. For items originating within our solar system, this speed is basically nil. They remain tied by gravity and will circle back eventually, regardless of whether their loops span millions of years. 3I Atlas, on the other hand, shows a V infinity around 25 kilometers, irrefutably proving its external provenance. To grasp the scale of this speed, note that Earth circles the Sun at roughly 30 kilometers. 3 Atlas hurtles through our system at a pace almost matching our planet's orbital motion around its Sun. This represents the impetus from an alien realm, a dynamic imprint from a birthplace where distinct physical laws shape the interplay of pull and movement. The very method of its detection underscores the scarcity of such interstellar travelers. The ATLAS survey, an acronym for Asteroid Terrestrial Impact Last Alert System, comprises 4 automated telescopes built to survey the whole observable sky twice nightly, seeking out asteroids that could pose threats to Earth. Over almost 10 years, after covering countless square degrees and recording hundreds of thousands of items, ATLAS has identified precisely 1 verified interstellar interloper. These figures are stark. Such objects might be 1,000,000 times less common than ordinary near-Earth asteroids. This scarcity doesn't imply that the void between stars is barren, far from it. Models predict that each cubic light-year in our local galactic region ought to harbor thousands of interstellar debris, pieces hurled out from other planetary setups during their tumultuous early development stages. The challenge lies in spotting them. These bodies are dim, swift, and trace paths that whisk them across our inner solar system for just short intervals. By the moment we detect them, they are frequently already speeding off into the distance. The breakthrough in broad-area astronomical surveys has at last equipped us with the means to locate these wandering space travelers. PanSTARRS, the Panoramic Survey Telescope and Rapid Response System, identified 1 IUMA back in 2017. The Catalina Sky Survey uncovered 2I Boris in 2019. These days, Atlas has yielded 3I Atlas. Each find demanded automated setups able to sift through thousands of images nightly, cross-checking them with star catalogs and highlighting the few shifting entities warranting closer human scrutiny. The validation procedure adheres to a strict regimen that could hold up in any legal setting. Preliminary spotting prompts swift subsequent viewings to determine key orbital parameters in mere days. Facilities around the globe supply location data that refine the path. Specialized orbital computation programs determine the optimal trajectory, evaluating if the path aligns with origins in our solar system or demands an extrasolar origin. Only after various separate reviews verify hyperbolic paths and rule out every feasible local source does an item gain interstellar status. The labeling practices mirror this meticulous checking. The I prefix for interstellar is granted solely following exhaustive examination. 1I for Oumuamua, 2I for Boris, 3I for Atlas. Every numeral signifies not merely a find, but a validated instance from the enormous array of rubble drifting amid the stars. Still, these 3 verified arrivals suggest a far greater array lurking undiscovered. The Rubin Observatory, now being built in Chile, is set to launch in 2025, boasting scanning prowess that outstrips all existing setups put together. Its expansive imaging device will chart the full southern heavens every 3 nights, with acuity sufficient to pick up interstellar bodies years prior to their closest solar approach. Models predict Rubin could uncover between 1 and 70 such interstellar arrivals annually, turning these uncommon celestial flukes into standard research prospects. The science behind interstellar classification holds deep significance. These entities serve as preserved relics from distant stellar realms, retaining molecular and atomic markers from world-building settings we'll never reach. Every arrival acts as a specimen brought right to us, bearing clues on circumstances near suns, potentially hundreds of light-years off and billions of years less aged than ours. The hyperbolic routes also imply just a single shot to examine each one. In contrast to recurring comets that loop back for ongoing study, interstellar bodies offer one-off meetings. The observations collected amid their fleeting transit through our detection range form the sole details we'll possess on these specific bits from the cosmic junkyard. As 3I Atlas presses on its hyperbolic path to perihelion, its extrasolar origins stand undisputed. The enigma isn't its provenance from another stellar setup. The trajectory calculations establish that beyond doubt. The puzzle concerns the nature of the star system that spawned such an odd drifter and the insights its peculiar makeup offers into world-building in realms wholly alien to ours. Part 7. 3 visitors, 3 personalities. The cosmos displays a quirky wit, evident nowhere more than in the lineup of interstellar intruders that have entered our solar system. Within under 10 years, we've welcomed 3 verified outsiders from foreign stars, each showing up with a character so unique that they appear crafted to challenge all our preconceptions about the void among the stars. This saga began with 1I Oumuamua in 2017. It was like an enigmatic outsider strolling into a quiet rural pub, expressionless and aloof. Telescopes revealed no coma, no tail, and no detectable gas emissions. Instead, there was just a rotating cigar-like form gleaming under sunlight, as if made of burnished steel. Its path seemed utterly ordinary at first, right up until it inexplicably sped up as it departed the sun. That boost was modest yet detectable, roughly 1/110,000th of Earth's gravitational pull. Still, it defied all predictions for how lifeless space rocks ought to act out there. Debates ignited across the scientific world. Theories ranged from unusual processes like hydrogen venting from hidden ice layers to light pressure acting on an exceptionally shiny exterior, and even wilder notions of light sails or magnetic influences. The speedup was genuine, verified by various observatories, though the reason stayed frustratingly out of reach. A single 1I Oumuamua had transformed the rules of orbital mechanics into a gripping whodunit, departing for the depths of interstellar voids with far more enigmas than resolutions. Next arrived 2I Borisov in 2019, showing up like an old acquaintance laden with unusual treasures. At last, an extrasolar guest that acted the part of a classic comet. It displayed a vivid coma, a clear tail, and consistent releases of water vapor and particles. Everything experts anticipated from a relic of ancient frozen matter, yet 2I Borisov brought its own elemental twist, levels of carbon monoxide vastly higher than those in our solar system's icy wanderers. The proportion of carbon monoxide to water hinted at origins in a chillier setting than our system's fringes, maybe orbiting a star ringed by a broader belt of frozen debris. Enter 3E Atlas now, as the climactic chapter in this cosmic tale, its makeup seeming intent on disrupting the trends we were starting to discern. While Oumuamua emitted no gases and Borisov brimmed with extra carbon monoxide, 3I Atlas takes the lead with carbon dioxide. This sequence from zero emissions to surplus carbon monoxide to carbon dioxide prevalence points to origins in such varied settings that these intruders could hail from entirely separate realms. The physical differences are just as compelling. Oumuamua's stretched, spinning outline evoked either a broken-off piece of nature or perhaps a more structured creation. Its 10:1 length-to-width proportion was unusually sharp, even for asteroids, sparking talks of possible artificial design. In opposition, 2I Borisov looked entirely standard, a near-round core enveloped in an even coma, with a classic tail pointing away from the sun. 3 Atlas bridges these in the most baffling manner. Its coma remains tight and ball-shaped, implying an intact core over a shattered one. However, the faint tail that appeared in imaging from late August feels oddly subdued next to 2I Borisov's bold stream. The form indicates targeted, restrained venting instead of the bursts common in comets nearing their solar closest approach. Estimates of their dimensions highlight yet another layer of variety. Oumuamua measured about 400 meters long, yet a mere 40 meters wide, a stellar pin. 2I Borisov's core came in at around 0.5 kilometers in diameter, standard for a medium comet. 3I Atlas lands in the middle ground, capped at 5.6 kilometer maximum, though it could be considerably tinier. Every one of these probes, a distinct size, ranged from the galaxy's wandering fragments. Most captivatingly, they showed up under wholly distinct visibility and detection conditions. Oumuamua was detected as it hurtled outbound from the sun, stumbled upon by chance in standard asteroid scans. 2I Borisov, meanwhile, was caught inbound on its trajectory. In the distant reaches of the outer solar system, this setup provided ample time for in-depth planning. 3I Atlas arrived at an ideal position, distant enough for strategic observation scheduling, yet near enough to launch intensive examinations right away. The molecular traces suggest origins in 3 separate settings. Oumuamua's absence of noticeable gas emissions could point to alteration by cosmic rays from space, total loss of volatiles, or birth in an exceptionally arid area of its home star system. Borisov's elevated levels of carbon monoxide imply it formed in the frigid fringes of a young planetary disk. Meanwhile, 3I Atlas's prevalence of carbon dioxide indicates moderate temperatures during its creation, possibly in a region where water stayed gaseous while CO2 was able to solidify. These variations in behavior go further than mere composition, touching on core physical principles. Oumuamua's puzzling speed-up implied influences outside standard gravity, such as undetectable venting, light pressure on its odd exterior, or forces we still can't pinpoint. Borisov adhered to standard comet dynamics, its path aligning perfectly with orbital predictions without any odd anomalies. So far, 3I Atlas seems to follow gravitational norms, yet its expansive CO2 envelope raises questions about how diminutive cores produce such massive vapor halos. The impacts of viewing angles are significant. Our perceptions hinge completely on positioning, timing, and the capabilities of our telescopes. Oumuamua's apparent inactivity might have appeared quite active if spotted during an outburst period. Borisov's classic look could have seemed peculiar from another viewpoint. 3I Atlas's faint trail might appear far more striking from Mars's vantage during the October flyby. Still, these 3 distinct traits, the enigmatic speedster, the CO-rich traditional comet, and the CO2 riddle, already suggest a huge range of interstellar variety yet to uncover. If the initial trio of cosmic travelers differs so much among themselves, what surprises will the following ones bring? Every such object acts as a snapshot from varied planetary building zones, bearing chemical markers that reveal the heat profiles and makeup of far-off systems we'll never directly observe. The sequence from Oumuamua to Borisov to 3I Atlas feels like the cosmos deliberately testing each of our ideas about rogue space rocks. Just as we start to grasp the pattern, another arrival upends the definitions completely. With 3I Atlas nearing its solar alignment, we ponder if its quirky traits signal the start of something even odder, or if we're just realizing how incredibly varied in chemistry the void between stars truly is. Part 8 delves into the motion mysteries. The cosmos often conceals its deepest enigmas in the tiniest breaks from the norm. This rings especially true in the delicate interplay of forces steering how these wanderers navigate our solar neighborhood. At heart, 3I Atlas's tale is one of physics on the move, of minuscule thrusts that might unveil key insights into the essence of interstellar material. Oumuamua set the pattern for cosmic intrigue by speeding up from the sun in ways that ignored pure gravity calculations. The shift was slight, around 10 micrometers per second, squared roughly 1100,000th of Earth's pull at the surface, but steady and trackable over weeks of monitoring. Various facilities verified the boost's existence, turning a routine orbit issue into an ongoing enigma that inspires studies even now, years on. The speed-up wasn't haphazard. It exhibited a distinct pattern indicating outgassing from the hemisphere, oriented toward the sun. Yet, this is precisely what rendered Oumuamua profoundly puzzling. Observations from no observatory revealed the expected gases or particles linked to such activity. The body gained speed akin to a comet while resembling an asteroid, sparking a puzzle that compelled scientists to explore ever more unconventional theories. Certain experts theorized that Oumuamua could be releasing hydrogen, an exceedingly sparse and elusive substance capable of driving the speed-up sans any noticeable coma. Alternative ideas pointed to solar radiation pushing against an exceptionally shiny exterior as the cause of the detected path. The wildest ideas touched on engineered beginnings, yet these stayed well beyond accepted scientific views. In comparison, 3 Atlas has displayed no similar speed-up irregularity to date. Its course aligns closely with gravity-based forecasts, adhering to the even hyperbolic route prescribed by Newtonian principles within the limits of measurement precision. However, this seeming regularity could prove deceptive. The extra-gravitational influences impacting Oumuamua only surfaced after prolonged monitoring as it receded from solar pull. 3 Atlas continues heading toward perihelion, with the most insightful data likely arising around and beyond its nearest sun pass. The composition of 3 Atlas implies that should such forces appear, they would likely adhere to a pattern quite distinct from the hydrogen release idea tied to Oumuamua. Sublimation of carbon dioxide yields far heavier particles compared to hydrogen, resulting in thrust that's simpler to spot, though it relies on distinct physical mechanisms. Should 3 Atlas display detectable speed-up, it might unlock insights into whether Oumuamua's actions were singular or a typical trait among interstellar travelers. The perspective from Earth introduces further intricacies to motion studies. Anti-solar tails might seem squeezed or outright hidden based on our viewing angle against the comet's path. The extension of the coma toward the sun, spotted by Hubble in 3 Atlas, initially baffled watchers anticipating outflow away from the sun instead of inbound. Nevertheless, dynamics of gas in 3 dimensions can produce visual deceptions, making substances in intricate flows seem to head in unexpected ways when viewed flat on the sky's canvas. The vast carbon dioxide coma raises its unique motion riddle. In what way does a core just kilometers wide sustain a releasing zone spanning hundreds of thousands of kilometers? The underlying principles require either a surface of exceptional vigor, possibly 100-fold more efficient per square unit than ordinary solar system comets, or a process spreading gas-generating stuff over a far broader area than the core alone. A potential scenario posits 3 Atlas as a scattered collection of tinier pieces, with each venting separately to form the widespread release zone. Yet, under that scenario, imagery ought to reveal breakup signs, like several bright spots or stretched forms hinting at separate bodies. To date, Hubble's detailed pictures reveal none of that. A further account draws on the interplay of venting and solar wind. When carbon dioxide particles flee the core, sunlight's UV rays can charge them up, forming ions that engage the sun's magnetic lines. Such electric-magnetic effects might propel the vapor to speeds well beyond basic heat-driven spread, possibly accounting for the huge reach of the carbon dioxide haze. The spin condition of 3 Atlas stays undetermined, yet it might offer vital hints into motion mechanisms. Most small irregular rotations often arise from outgassing forces, where bursts of expelled gas function like miniature thrusters, slowly altering the body's rotational behavior. Given the intense activity implied by 3I Atlas's expansive coma, one would expect substantial torque effects manifesting as fluctuations in brightness over extended photometric monitoring. However, the light curve data reveals impressive steadiness, lacking any rhythmic dips or peaks that signal erratic spinning. Such consistency might indicate a leisurely rotation rate, an alignment close to pole-on that keeps the visible profile constant during turns, or an exceptionally even surface where spinning yields no noticeable light shifts. These scenarios each point to distinct clues about the body's makeup and formation history. Observations from the Transiting Exoplanet Survey Satellite, TSS, have suggested potential outbursts even at vast separations from the Sun, where 3I Atlas was initially spotted. Should these signs hold up, it would imply the interloper was already venting material beyond Jupiter's orbit, pointing to either an exceptionally fragile makeup or some activation process unrelated to mere sunlight warmth. As 3I Atlas nears its closest solar approach, the motion-related puzzles will grow ever more pressing. Might it display the enigmatic non-gravitational push seen in Oumuamua? Could the shape of its dust envelope expose the gas streams accounting for its vast vapor halo? Such revelations might reshape our grasp of interstellar objects, navigating unfamiliar stellar environments far from their origins. The underlying science unfolds before us live, etched in trajectories and emission lines. We are witnessing forces set in motion around a distant sun, eons ago, now culminating under our own star's gravitational pull. Now, on to Section 9, the worldwide vigil. What's being watched by whom and at what times? Astronomers everywhere have turned 3I Atlas into the most closely tracked extrasolar wanderer ever, directing a planet-spanning scrutiny effort that unfolds like a harmonious orchestra of research spanning landmasses and satellites alike. Leading space organizations and earthbound scopes have united in what stands as our species' most unified push to decode one tiny traveler speeding past our stellar turf. NASA's Science Mission Directorate set up the guiding structure, coordinating a broad multi-mission strategy that draws on all resources at hand. Hubble's orbital eye offers top-tier sharp images, following shifts in the envelope's form and limiting estimates on the core's dimensions beyond any terrestrial tool's reach. The James Webb Space Telescope supplies infrared spectral analysis with the finesse to pick up faint vapors at levels of mere parts per million. Swift keeps tabs on UV outflows that expose the chemical reactions dismantling compounds in the haze. The Forecast instrument has stepped up as a surprise standout in this watch effort. Built to chart the infrared cosmos for big-picture universe probes, its broad-view strength turned out ideal for outlining the massive CO2 plume encircling 3I Atlas. The partnership of Webb's detailed spectral insights and SphereX's expansive surveys has yielded a full view of molecular makeup and layout alike. Insights impossible from any one device. Telescopes on the ground across the globe have synced up via the International Astronomical Union's Quick Alert systems. Gemini North on Hawaii snagged the early shots, exposing 3I Atlas's tight dust shell. Its counterpart, Gemini South in Chile, delivered the end-of-August deep exposures that verified the faint tail pointing away from the sun. The Palomar Observatory's next-generation Palomar Transient Survey, adds ongoing monitoring through photometry and astrometry, continues to monitor variations in brightness while sharpening the orbital parameters with every new data point. However, the schedule for these observations is heavily influenced by an inevitable celestial reality: solar conjunction. As 3I Atlas nears its perihelion on October 29, 2025, the alignment of Earth with respect to the Sun produces an observation setup that's equally aggravating and evocative. Just when this interstellar object enters its peak activity, it will vanish into the Sun's blinding light, out of reach for all ground-based tools for almost 2 months. This dark interval stands as one of the most exasperating quirks in astronomy. The very moment when solar warmth ought to push 3I Atlas to its height of vigor, when the core's heat surges and gas emissions hit their zenith, will stay hidden from Earth's view entirely. We'll forgo the climax of this stellar spectacle, able only to examine the prelude and the consequences. Its return in early December signals the start of the closing chapter. 3I Atlas will appear in the morning sky within Virgo, then ascend toward Leo over the following weeks. At that stage, it will hurtle from the Sun at speeds over 150,000 mph, dimming progressively each evening as it heads back into the void between stars. The efforts after perihelion will involve a frantic battle against fading signals and increasing separation, with detection power dropping off sharply as the object pulls away. Still, this tough schedule has sparked innovative approaches that highlight the resourcefulness of contemporary space research. The HiRISE instrument on the Mars Reconnaissance Orbiter offers a rare chance to view 3I Atlas from a Martian vantage. On October 3, 2025, the object will come within 29 million kilometers of Mars, possibly enabling orbiting instruments to snag photos amid Earth's blind spot. The detail won't match Hubble's sharpness, yet it could deliver vital insights while terrestrial scopes remain sightless. A number of probes journeying in the distant solar system have emerged as possible aids in the watching effort. NASA's Psyche, en route to a metal-rich asteroid, will swing by about 0.3 AU from 3I Atlas on September 4, 2025. The European Space Agency's JUICE probe, destined for Jupiter's satellites, might try distant imaging near its November 4 flyby. The OSIRIS-APEX mission could even join in with potential snapshots from late 2025 onward. Although the alignment issues persist as hurdles, the collaboration reaches past standard skywatching tools. Global radio arrays are scanning for radio signals that could reveal electric discharges or odd solar wind effects. Radar setups on planets aim to ping the core and gauge its dimensions and spin via signal bounce-back times. Even citizen astronomer groups have rallied to supply photometric data that patches holes in expert surveys. This global teamwork has crafted a viewing plan akin to strategic planning in warfare. Oversight panels at key facilities have approved urgent time blocks, interrupting established studies to seize this stellar chance. Protocols for sharing info let spectral readings from one site sync right away with visuals from elsewhere, boosting the impact of every dataset through combined analysis. The European Space Agency's Planetary Defense Office has orchestrated pursuit activities that go well beyond mere interest in discovery. Though 3I Atlas presents zero danger to our world, the methods honed for tracing its path and forecasting its actions will offer essential tools for upcoming defense against cosmic hazards. Every aspect of tracking the object's position and speed feeds into simulations that might one day shield Earth from more hostile cosmic intruders. With the viewing period closing in on solar conjunction, worldwide scrutiny has hit a frantic peak. Observing slots, which normally demand years of rival bids, are now handed out on a weekly basis. Analyses that customarily span months are being squeezed into mere days. The Global Astronomy Network has basically sounded the alarm on 3I Atlas as a stellar crisis, not due to any threat it carries, but because it's a chance that won't repeat. The object's return in December will put this international effort to the ultimate test. Can we sustain such rigorous surveillance when it's dimmer and farther off? Will the chemistry after perihelion uncover mysteries that pre-perihelion scans merely suggested? The coming months will decide if this historic watch yields game-changing discoveries that reshape our grasp of deep space beyond our system. Part 10. Is a rendezvous feasible? The alluring idea of pursuing an interstellar guest via a rushed probe slams into the harsh equations of orbital paths and the brutal limits of launch tech. Still, the sheer unfeasibility of catching 3I Atlas has sparked some of the boldest spacecraft concepts in years, ideas that stretch what's doable with today's hardware to the edge. The core issue boils down to timing and speed. When spotted, 3I Atlas was already hurtling into the solar system's core at more than 200,000 km/h. A pursuit craft would have to align not only with that massive pace, but also the exact path, including its angle and tilt across 3D space. The power demands for such a route lock it into sci-fi territory given our present engines. An Earth-launched chaser would call for velocity shifts dwarfing our strongest boosters by 10 times or greater. Even supposing we mustered the push, the journey to a meeting spot would drag on for years, long after 3I Atlas had vanished into the void, outpacing any realistic chase. Yet such barriers have never deterred space innovators from envisioning solutions. Various teams have probed options leveraging probes already cruising the solar system. NASA's Psyche, en route to a metal-rich asteroid, will zip by within 3 AU of 3I Atlas on September 4, 2025. Though not built for comets, Psyche's tools like imagers and analyzers could potentially snag key info on the close pass. The JUICE mission, ESA's probe to Jupiter's icy satellites, offers yet another stroke of lucky observation. Its path will bring it near enough to 3I Atlas on November 4, 2025, right when ground telescopes lose sight amid solar glare. The probe's high-end cameras and spectral gear might fill that critical blind spot with vital readings. Despite hurdles in alignment and ops, the wildest idea targets NASA's Juno, now circling Jupiter to probe the planet's core. A group from the Harvard-Smithsonian Center for Astrophysics, spearheaded by stargazers, has mapped out a precise path tweak to steer Juno into a March 2026 brush with 3I Atlas. The scheme: the mission would harness Jupiter's immense gravitational pull as a celestial catapult, boosting speed via an orbital maneuver that capitalizes on the probe's nearness to the colossal world. The concept behind the Juno intercept plan sounds like a dream of space exploration brought to life. The probe would have to perform a meticulously scheduled engine firing while immersed in Jupiter's gravitational depths, tapping into the gas giant's orbital momentum to speed up along a path aimed at rendezvous. Precision in timing would be essential. A delay of even hours could render the meeting unfeasible. Nail the operation flawlessly, and Juno might turn into the first human-made craft to achieve a near pass by an object from beyond our solar system. Still, ideas like this stay stuck in the planning phase, limited by practical challenges that go well beyond just path calculations. Juno's ongoing assignment wraps up in 2025, and altering its course would demand clearance from NASA leadership, thorough operational design, and probably review by Congress. The probe's worn-out components and scarce propellant further complicate this ambitious idea. The flyby of Mars on October 3, 2025, presents the most feasible chance for up-close study. With 3I Atlas sweeping just 29 million kilometers from the rusty world, the Mars Reconnaissance Orbiter's HiRISE instrument might snap photos with detail nearing 30 kilometers per pixel. Though not as sharp as Hubble's views, it would offer a fresh angle at a key moment when ground telescopes on Earth can't see it. The OSIRIS-APEX project, initially aimed at probing the asteroid Apophis, pops up in various scholarly articles as a possible asset for monitoring 3I Atlas from late 2025 onward. Its array of tools, built for intimate asteroid analysis, could deliver remarkable insights into the makeup and traits of such an extrasolar guest's exterior. That said, the schedule and flight path limitations turn any such monitoring into pure conjecture. Peering ahead, the European Space Agency's Comet Interceptor effort stands out as our strongest shot at a purpose-built chase of an interstellar wanderer. Set for liftoff in 2029, this quick-reaction venture can pivot to promising newcomers, such as fresh interstellar finds. The craft will linger in a stable halo orbit, poised to dash off after the next intriguing spacefarer that shows up. Since the spotting of Oumuamua, research on pursuit missions for interstellar objects has surged, with publications delving into options from light sails to nuclear engines to slingshot paths involving chains of planetary assists. This work acts as groundwork for viable future ventures, outlining the tech and coordination needs for expeditions that aren't built yet, but could one day take flight. The power demands for catching interstellar targets highlight how distinct they are from everyday solar system destinations. A trip to Mars calls for about 6 kilometers of delta V, while skimming Jupiter takes roughly 12 kilometers, but snagging something like 3.3 Atlas would require delta V nearing 50 kilometers or higher. Chemical thrusters can't handle that, so it would need atomic drives, light sails, or drive systems still in the realm of theory. Nevertheless, the rewards of a thriving intercept would reshape our knowledge. Up-close scans of an interstellar arrival could uncover isotope patterns reflecting its birth star's surroundings, outer layers holding clues to foreign disk chemistry, and build qualities showing how tiny objects endure travel across stellar voids. That kind of information would justify years of Earth-bound research. These insights offer essential validation for concepts surrounding planet formation in settings vastly unlike our solar system. The harsh twist lies in the fact that every interstellar interloper acts as a pristine lab specimen dropped right at our threshold, but it zips by too swiftly for us to gather it effectively. It's as if scientists are peering out from their lab, eyeing precious artifacts marching by just beyond reach, near enough to tease, but beyond the grasp of today's tools. While 3I Atlas hurtles along its hyperbolic path en route to perihelion, analyses from the Intercept mission highlight our present constraints in a vexing way, while also sketching out exciting paths for what's ahead. Though we can't pursue this wanderer, these efforts are teaching us how to prepare for the subsequent arrival. Part 11. The Puzzle of Carbon Dioxide. Plausible Natural Origins in Play. The otherworldly composition of 3I Atlas resembles instructions from an extraterrestrial manual, featuring carbon dioxide in ratios that upend all our established frameworks for comet dynamics. Still, prior to exploring outlandish ideas, fundamental physical principles suggest multiple straightforward mechanisms that might yield this peculiar molecular profile. Every such mechanism uncovers deep clues about the birthplace of this traveler. The idea of a carbon dioxide snowline delivers one of the most refined accounts for 3I Atlas's atypical makeup. Within a protoplanetary disk, various gases solidify at varying radii from the host star, forming compositional layers as sharply defined as Earth's latitudinal weather zones. Icy water prevails in the frigid outskirts, yet carbon dioxide solidifies at milder intermediate chill levels. A body assembling slightly inward of the water snowline but beyond the carbon dioxide boundary would embed plentiful CO2 frost, all while staying mostly free of water. This setup situates 3I Atlas's origin in an area broadly similar to our own asteroid belt, sufficiently temperate for water to linger as gas, yet cool enough to let carbon dioxide crystallize from the vapor. That kind of setting would generate precisely the profile we detect: plentiful carbon dioxide frost with just traces of water mixing in. The birthplace amounts to an ideal stellar niche, shaped by thermal dynamics that prioritize carbon-rich gases ahead of water-based molecules. However, conditions around stars differ wildly across the cosmos, so the prevalence of carbon dioxide could stem from more unconventional birth scenarios. Variations in stellar size and brightness produce distinct heat distributions in their encircling disks. A dim, lightweight star could shift the carbon dioxide snowline nearer the core, expanding the territory where CO2 frost outshines water. On the flip side, a bright, powerful star could generate heat slopes that promote carbon dioxide buildup via wholly novel reaction routes. Another persuasive account for 3I Atlas's odd composition comes from radiation effects. Over its eons adrift in the void between stars, this object endured cosmic rays intense enough to obliterate any terrestrial life form. Energetic particles are capable of shattering atomic links, reshuffling molecular arrangements, and forging fresh substances via radiolysis, a radiation-driven alchemy functioning as an interstellar test chamber at the atomic scale. This kind of alteration might account for both the carbon dioxide surplus and the evident scarcity of water. Galactic rays could selectively erode water frost, sparing carbon dioxide mostly unharmed. Alternatively, they could transform basic carbon compounds into CO2 via intricate chains of reactions. The red hues spotted by Spherex and 3I Atlas's spectral data align with such radiation influences, indicating that its exterior has truly undergone molecular changes amid its cosmic voyage. The insulating crust theory tackles one of the most baffling features in the conduct of 3 Atlas. Why does it exhibit such intense carbon dioxide release even as signs of water stay persistently faint? Experiments on similar substances indicate that mantles loaded with organics can develop over frozen exteriors, forming barriers that hinder the evaporation of volatiles in targeted manners. Should 3 Atlas have acquired such a covering amid its voyage through interstellar space, ample water ice could lurk just under the exterior, yet blocked from turning into vapor by the material above it. Carbon dioxide, being far more prone to evaporation than water under identical conditions, might seep out via fissures or sparse areas in this barrier, yielding the detected release profile. This scenario accounts for why Webb identifies plentiful carbon dioxide vapor, whereas FERC spots proof of water ice in its solid form. The water exists, but it's confined beneath a superficial coat that permits carbon dioxide to vent while holding back the rest. The concept of icy fragments, put forward by scientists examining the sprawling gas halo, proposes a wholly distinct process. Instead of one cohesive core, 3 Atlas could consist of assorted carbon dioxide-laden ice pieces bound loosely by gravity and adhesion. With rising solar warmth, these bits might drift apart and vaporize on their own, generating the vast carbon dioxide envelope via widespread venting over a far broader area than any lone core might achieve. Such a breakup framework would simultaneously clarify multiple odd findings: the widespread gas halo, the steady luminosity amid evident vigor, and the faint tail shape hinting at ejection of sizable dust grains. If 3 Atlas amounts to a drifting heap of carbon dioxide ice rubble, its actions would truly diverge from every known comet in our solar system's records. Thermal influences add further insight to the enigma. At the present solar separation of 3I Atlas, nevertheless, the sheer number of these possibilities generates a fresh enigma. Given the multitude of credible theories at hand, how can we pinpoint the right one or the ideal mix that truly captures the reality of this cosmic drifter? Part 12. From whence did it originate? Pinpointing the stellar origins of 3 Atlas resembles cracking a homicide investigation where the incident occurred light-years distant and the clues are embedded in orbital dynamics spanning immense cosmic eras. Still, concealed in the intruder's path lie dynamic hints that direct us to a particular group of stars, and thus to a defined period in the evolution of our galaxy. The idea of the thick disk has surfaced as the frontrunner in explaining 3I Atlas's beginnings. The Milky Way, our home galaxy, features multiple unique groups of stars. The thin disk, home to our Sun, holds comparatively youthful stars loaded with heavy metals. The thick disk, filled with ancient stars born when the galaxy was maybe only half its present size, and the venerable stellar halo, harboring the galaxy's most primordial and metal-deficient stars. Every group navigates the cosmos with distinctive speeds and orbital behaviors that mirror the gravity fields of their birthplaces. The motion profile of 3I Atlas, its pace and bearing compared to the standard local reference, indicates it belongs to the thick disk group. These stars took shape about 8 to 12 billion years back, in the phase astronomers term cosmic noon, when starbirth across the cosmos hit its zenith and the creation of heavy elements swiftly boosted the content of the space between stars. Should 3I Atlas have sprung from this star-filled setting, it embodies substance that has roamed the galaxy long prior to Earth's emergence. An origin in the thick disk holds deep significance for grasping how planets arose in the universe's infancy. Stars there coalesced from gaseous nebulae poorer in heavy metals than the conditions surrounding our sun's formation. This diminished metal content likely influenced the makeup of nascent planetary disks, possibly promoting carbon-rich gases over those laden with oxygen, which might account for 3I Atlas's peculiar makeup. Yet the tale of its beginnings goes further than mere star groupings, encompassing the fierce dynamics that first hurl stuff from solar setups. Tugs from massive planets can fling lesser objects into hyperbolic paths, propelling them into the void between stars at speeds tied to the precise setup of the clash. Nearby passes by other stars can likewise unsettle solar systems, peeling off edge disk matter to fuel the roster of interstellar rubble. Such expulsion methods foster a Darwinian filter in the interstellar realm. Just items within certain dimensions, makeups, and builds can endure the brutal launch and the ensuing eons of travel through space. 3 Atlas stands as a veteran of this galactic sifting, bearing molecular and structural marks that reveal its birthplace and endurance saga. Surveys of the trio of verified interstellar intruders uncover a detection skew that muddies efforts to deduce their backstories. We have spotted one item showing no evident gas release, another boosted in carbon monoxide, and yet another ruled by carbon dioxide. This could mirror the actual variety of space-floating wreckage, or it may stem from the quirks of our ongoing observation tools. Items varying in scale, outburst styles, or incoming angles could elude our scopes entirely. The broader galactic backdrop introduces yet more doubt to these origin narratives. 3 Atlas. It has journeyed across the cosmos for millions of years, encountering gravitational influences from numerous star systems along its path. These interactions have slowly altered its course, wiping out the distinctive motion signatures that might enable an exact trace back to its birthplace. Although we can determine the broad category of stars from which it probably originated, identifying the precise stellar system could prove unattainable using available information. The elemental indicators offer tighter boundaries on its birth setting. The prevalence of carbon dioxide demands specific temperature and pressure levels found solely in certain regions near evolving stars. Should 3I Atlas have solidified directly from vapor in a young planetary disk, the physical conditions would need to have prioritized carbon dioxide formation over water ice, implying either atypical chemistry in the disk or condensation at a particular orbital radius where such factors occur organically. Isotopic compositions might deliver the definitive proof of 3I Atlas's provenance. However, analyzing isotopes in such a dim, remote body strains the boundaries of today's observational methods. Various stellar surroundings generate unique isotopic markers in their worlds and remnants, yielding molecular signatures that could not only specify the class of star system where 3I Atlas arose, but also potentially reveal the exact mass, age, and metal content of its host star, the Vera C. Rubin Observatory's ongoing survey of the sky and time, set to commence in the near future, holds the potential to elevate studies of origins from isolated examples to robust statistical analysis with the power to spot scores of interstellar wanderers annually. This facility will amass a dataset substantial enough to uncover group characteristics and compositional trends that isolated cases like 3I Atlas merely suggest. Initial reports in certain publications suggesting an origin beyond our galaxy for 3I Atlas seem to stem from unsubstantiated conjecture instead of established agreement among experts. The motion data strongly indicates a source within the Milky Way, probably from the thick disk component. Though the galaxy's scale defies human grasp, it remains finite, and the principles of orbital motion impose definite limits on the distance 3I Atlas could have covered while following its detected path. The moment of 3I Atlas's entry into our solar system could simply be happenstance, or it might signal underlying rhythms in galactic motion that remain beyond our current insight. Assuming the thick disk as its starting point, 3I Atlas embodies ejecta from a planetary setup billions of years in the past, drifting through the galaxy amid eras of cosmic obscurity. It has endured supernova blasts and the transformative phases of stellar life cycles that repeatedly remolded the galactic backdrop. Through our examination of this intruder's makeup and movement, we are effectively performing large-scale cosmic archaeology, deducing traits of long-lost planet-building zones from the fragments they discarded. 3I Atlas serves as a relic from the past, yet one that is spun through the void for so extended a period that its internal materials have undergone modifications from mechanisms we are just starting to unravel. Observations in December as 3I Atlas reappears after solar conjunction will offer vital evaluations of theories about its beginnings. Should the chemistry following perihelion display expected shifts aligned with thermal simulations, it would bolster standard models of ice formation. If the composition persists in defying expectations, it could point to birth mechanisms or later alterations that surpass our existing conceptual models. Part 13, the Avi Loeb chapter, open-minded and contentious. Within contemporary astronomy, scant individuals provoke as much fervent discussion as Avi Loeb, the Harvard astrophysicist, whose readiness to explore non-traditional ideas has positioned him as both a target of dispute and an advocate for innovative science. Open-mindedness. Loeb's examination of 3I Atlas highlights this intricate heritage. Grounded in rigorous empirical data, it ventures into daring territory with its conceptual ramifications. Loeb dove into 3 Atlas right after its initial sighting, producing a collection of in-depth articles that monitored the intruder's shifting visual traits with the acuity of an investigator chasing clues. His piece from August 27th stood out as especially insightful, as it identified the subtle anti-solar tail overlooked by standard surveys. Just a few days later, Astronomer's Telegram entry 17363 validated Loeb's foresight precisely. That delicate tail formation existed, apparent only to analysts who stretched their processing techniques to the edge of visibility. Yet Loeb's take on 3I Atlas goes well past verifying typical comet-like traits. Drawing from luminosity projections and light-scattering simulations, his assessments of its core size point to a body possibly spanning dozens of kilometers, vastly exceeding Hubble's ceiling of 5.6 kilometers. This gap carries real weight. It points to entirely novel dynamics shaping the object's response to solar radiation. Either Loeb's illumination frameworks are flawed, or 3 Atlas exhibits light-reflecting qualities unseen in anything from our solar system. Data from the FARO spectral surveys underpins several of LOE's boldest assertions. The enormous carbon dioxide envelope, stretching almost 250,000 miles from the core, signals an outburst magnitude that upends standard evaporation theories. Loeb stresses that generating such vast gas volumes from a compact center demands either unprecedented vigor or processes spreading out the emission points over a far broader area than classic comet theories allow. Loeb's handling of the water vapor debate showcases the systematic rigor defining his work. Initial SWIFT scans indicated robust H2O output via hydroxyl radical signals, though follow-up SPHEREx surveys detected H2O traces far under the sensitivity limit. Instead of rejecting one side, Loeb weaves both findings into a unified explanation. 3 Atlas may harbor water ice deep inside, yet outer layer dynamics are blocking effective vaporization, accounting for the mismatch between anticipated and actual water readings. Loeb's work turns truly contentious in probing what he calls technological ideas behind 3I Atlas's conduct. Referencing the odd speed-up of 1 Oumuamua, he probes if standard laws of nature adequately cover the intruder's prolonged CO2 halo and peculiar shine. His computations indicate that natural venting alone may falter in justifying the massive vapor shroud, prompting thoughts of extra power inputs fueling the displays. The idea of inherent glow stands as Loeb's most audacious proposal. Should 3 Atlas harbor inner power beyond mere sun-warmed evaporation, be it from nuclear breakdown, electric effects, or stranger forces, it might sustain outburst rates beyond what passive ice-to-gas transitions can achieve. That hidden power could drive the sprawling CO2 output without showing up in routine skywatching tools. Loeb's path-tracking review layers more mystery onto his tech-oriented ideas. He observes that 3I Atlas's route across our star system features alignments that maximize viewing chances from our planet. as though the course was crafted for peak research value. Sure, randomness could explain it, but the cosmos never lacks for cosmic alignments of this sort prompt intriguing questions. Lowe suggests that we ought to at least explore if such ideal positioning could hint at deliberate guidance. The interception strategies that Lowe has helped develop stand out as his most tangible input to the study of 3 Atlas. Collaborating with experts in orbital paths, he has sketched out precise plans for rerouting NASA's Juno probe to rendezvous with the intruder in March 2026. These ideas encompass exact thrust schedules, velocity change needs, and tool functionalities that would yield groundbreaking near-up-close insights into an extrasolar wanderer. Still, Loeb admits the far-fetched quality of his bolder ideas. In his writings, he always presents tech-based ideas as options for scrutiny, not as settled truths. True science requires examining every option that aligns with the evidence, including those that upend standard views on what cosmic junk ought to resemble. Coverage in the press about Lowe's 3I Atlas breakdown has stuck to familiar tropes, with titles screaming of potential threats from advanced tech that twist his nuanced guesses into overblown tales of extraterrestrial arrivals. This kind of reporting warps both Lowe's core points and the essence of probing ideas through evidence. Lowe floats tech scenarios not out of conviction in their reality, but as viable counters to routine theories that can be put to the test. His handling of 3 Atlas embodies a wider outlook on how research ought to tackle odd findings. Instead of cramming data into outdated models, Lowe pushes for broadening those models to include ideas that at first glance appear far-fetched. This way of thinking echoes past successes. Plenty of major advances in stargazing started with sightings that clashed with established theories. The verification steps that Loeb describes for separating natural from artificial origins offer a clear path to cracking the 3 Atlas puzzle via hard evidence, not just favored notions. Frequent light measurements might uncover if the thing's glow shifts in patterns suggesting man-made lights. Spectral scans could spot signatures of unusual reactions in its makeup. Up-close flybys from probes could gauge traits beyond the reach of far-off telescopes. Lowe's partnerships with established observation groups highlight his dedication to fact-driven exploration over wild guesses. His assessments of scale and composition draw from the identical datasets that peers examine. Yet his openness to offbeat interpretations frequently yields fresh insights. The ongoing discussion around 3 Atlas has gained depth from this range of views. Even amid the sparks they ignite, the tight timeline for 3 Atlas sightings lends weight to Lowe's push for rigorous idea checking. With mere months left before the object vanishes into the void, the chance to collect game-changing proof is shrinking fast. To evaluate artificial origins properly, those checks need to occur right away, while 3I Atlas is still within range of our top tools. As the sun's alignment nears and viewing chances fade, Lowe's breakdown acts as both a key research piece and a deeper reflection on the heart of celestial investigation. His readiness to probe options that colleagues sidestep raises a fundamental issue about science's handling of truly puzzling evidence. Whether we ought to favor familiar theories that align neatly. Scientists should neither dismiss emerging concepts outright nor close off avenues that could transform our grasp of cosmic possibilities. The 3I Atlas debate might endure in memory not for the particular idea it sparked, but for the rigorous approach to inquiry it demonstrated. This equilibrium between reasoned doubt and true receptivity enables scientific advancement to push past the limits of established wisdom. Part 14. How might we verify or refute these ideas? The upcoming solar conjunction for 3I Atlas offers a perfect real-world test for celestial observers. Yet, its return in December will spark one of the most thorough observation efforts ever in the study of minor celestial objects. The challenges facing this extrasolar guest amount to a rigorous examination under scrutiny, pitting rival theories about its makeup against the unyielding judge of empirical evidence. Post-perihelion spectral analysis could unlock the chemical enigmas that have marked 3I Atlas from the start. Should standard sublimation dynamics control this object's actions, the proportion of carbon dioxide to water ought to shift in expected ways as it recedes from solar influence. The core's heat would have reached its maximum during the hidden closest solar approach, possibly shattering any protective outer shells that earlier stifled water release on the inbound leg. Spectra from December and January should reveal heightened water output if those blocking factors were at play. On the other hand, if carbon dioxide continues to prevail unaltered past perihelion, it might indicate a truly water-poor makeup or processes that sustain the imbalance irrespective of heat levels. That kind of stability would question traditional views on cometary gas release patterns and lend weight to unconventional accounts of 3I Atlas's traits. Frequent light curve tracking forms yet another vital check on rival notions. For a typical icy core with routine venting, its luminosity should exhibit foreseeable rhythms tied to spin and gas jets. Active comets usually show light changes over periods from hours to days, as spinning surface spots turn toward or from the sun. Lacking those shifts could point to exceptional evenness in surface materials or an angle of view that dampens spin-related effects. Even more strikingly, signs of engineered lighting or unnatural glows would appear as light swings, unrelated to solar warmth or positional factors. Such indicators would prove nearly impossible to mimic naturally, offering compelling proof for bolder interpretations. Photometric watches in December and January will basically keep 3I Atlas under round-the-clock watch, logging each brightness shift that might expose its true essence. Detailed imaging efforts with Hubble and major Earthbound scopes will follow changes in the surrounding dust cloud's form as 3I Atlas recovers from its solar close call. Standard venting theories forecast distinct dust ejection and tail formation sequences that grow clearer as the object pulls away from the sun. The form, direction, and expansion speed of tail features will yield precise indicators of whether 3I Atlas adheres to standard comet behavior or follows alternative principles. Observations from Mars on October 3rd give a rare chance to examine 3I Atlas from an off-world vantage while Earth-based views are blocked. Should the Mars Reconnaissance Orbiter's high-resolution instrument snag shots during the near pass, the results would impose key limits on coma architecture and behavioral patterns at the height of thermal strain. Observations from Mars will offer a starkly contrasting viewpoint to those from Earth, possibly uncovering imbalances or oriented phenomena hidden from our current viewpoint. Opportunistic flybys by spacecraft could deliver the strongest validations of 3I Atlas's character. The Psyche mission's September rendezvous, Jewish November surveys, and prospective OSIRIS APEX imaging in late 2025 all present chances for proximity-based assessments unattainable by Earthbound observatories. Data from these probes might image the core up close, gauge interactions with magnetic fields, and identify particle outflows that could differentiate organic from engineered beginnings. The James Webb Space Telescope's subsequent scans will extend infrared analysis to unprecedented levels of detail and clarity. Its prowess in spotting faint organic molecules, assessing isotopic compositions, and charting the spatial layout of gas outflows could yield the molecular clues required to separate competing origin theories. Should 3I Atlas display isotopic markers typical of the primordial galaxy, that would bolster the thick disk formation idea. Unusual isotopic balances could suggest alteration through unusual processes amid its trek across the stars. SphereX's ongoing surveys of the carbon dioxide nebula will examine if the vast outflow zone expands, contracts, or holds steady in scale as 3I Atlas navigates varied solar conditions. Standard outgassing theories forecast precise links between distance from the sun and coma extent, patterns that ought to appear if traditional physics dictates the object's conduct. Of utmost significance, spotting any non-gravitational motion would impose key limits on the forces propelling 3I Atlas's outbursts. Detecting those shifts demands extended, precise positional monitoring over months. By pitting actual trajectories against solely gravitational forecasts, any deviations in speed could reveal whether they're due to routine venting or stranger influences. Blending diverse methods, chemical analysis, motion studies, shape profiling, and light measurements will yield insights no isolated approach could attain alone. Organic accounts of 3i Atlas's actions generate clear, verifiable forecasts for how these metrics interconnect. Artificial origin ideas foresee alternate linkage schemes, forming branching paths where data steers us to reality. The viewing period from December to March marks our last shot to decode this specific star traveler. Beyond then, 3i Atlas will dim past the grasp of our finest instruments, hauling its enigmas into the stellar abyss. These pending probes of our guest embody both a prime research prospect and a duty to science, an opening to enrich our cosmic knowledge with vital evidence, and a mandate to chase it methodically and without bias. The cosmos has brought 3i Atlas to our stellar threshold for motives we might never grasp. How we react to this offering will shape if we leave wiser or just more puzzled. Part 15. The broader context, gearing up for what follows. The tale of 3i Atlas reaches well past one lone interstellar wanderer hurtling past our planets. It signals the dawn of a fresh phase in celestial studies, where the gulf among stars shifts from barren expanse to a bustling domain of roving planets and stellar rubble. As we grapple to comprehend this one, as we detect this interstellar visitor, we're also establishing the foundation to examine dozens more that are likely to be uncovered in the decades ahead. The Rubin Observatory's Legacy Survey of Space and Time is ready to transform our knowledge of objects drifting between stars thanks to its overwhelming volume of data. Starting full operations in 2025, its 8 4-meter mirror and 2 gigapixel camera will chart the whole southern sky every 3 nights, reaching detection thresholds that far surpass existing survey tools. Models predict this vast inventory might spot between 0 and 70 such wanderers annually, based on the actual sizes and behaviors of debris from other star systems. Shifting from rare one-off finds to robust datasets will reshape the field of interstellar object research. Rather than viewing every find as an isolated enigma, we'll start spotting trends, links, and overall distributions that uncover the core mechanisms driving the birth and development of planetary systems throughout the Milky Way. 13. Atlas, alongside Oumuamua and Boris, will act as the benchmark dataset for this emerging data-driven method of probing extraterrestrial remnants. The European Space Agency's Comet Interceptor mission marks our boldest effort yet to gear up for the next such arrival. Set to launch in 2029, this cutting-edge probe will station itself at the stable Lagrange point L2, about 15 million kilometers from Earth, standing by for promising targets. Should another interstellar object appear, and projections indicate it's inevitable, Comet Interceptor could pivot to a rendezvous path in mere months, not years. The core idea of the mission tackles the core difficulty of probing speedy interstellar intruders. Preparation must happen in advance, not in a frantic rush post-detection. The probe features an array of tools tailored for swift passes by untouched bodies, such as imagers that detail surface details, spectrometers for quick chemical breakdowns during close approaches, and collectors that snag and study the particles ejected by these cosmic travelers. The quick reaction protocols being built for interstellar objects hold value well beyond basic research. The monitoring networks that pick up these drifters also keep watch for dangerous near-Earth asteroids, blending planetary protection with studies of interstellar phenomena. The skills honed for tracking 3i Atlas-like fast orbital calculations, linking multiple telescopes, and adaptable observation slots will be essential for handling any potential collision risks down the line. Handling public interest in interstellar visitors demands a delicate mix of transparent science and thoughtful messaging. Every fresh find sparks press buzz about extraterrestrial sources, opening doors for learning but also risks of false narratives. The 3i Atlas saga has shown how vital it is to deliver prompt, straightforward scientific updates that highlight real unknowns without fueling hype that distorts public perception. The processing systems created for 3i Atlas have raised the bar for joint skywatching efforts. Blending inputs in real time from Hubble, Webb, Spitzer, and Earthbound scopes has fostered remarkable teamwork, where each tool's strengths bolster the rest. This integrated model offers a blueprint for probing upcoming interstellar objects, guaranteeing we extract the most insight from every fleeting visit. The collaborations between industry and universities built around 3I Atlas campaigns have pioneered innovative approaches to opportunistic target observations. The long-standing tradition in astronomy of meticulously scheduled, rigorously vetted observation schedules has turned out to be insufficiently agile for examining swiftly changing interstellar objects. Rather, we have crafted quick reaction procedures that allow us to repurpose key observatories in mere days following detection, converting rivalrous access to telescopes into unified hubs for scientific collaboration. The conceptual model for interpreting these interstellar objects has grown substantially since the finding of Oumuamua, drawing in knowledge from theories of planet creation, the study of life origins, and even hypothetical physical principles. 3 Atlas has contributed insights into carbon dioxide compositions to this model, offering a fuller view of the potential chemical settings in which fragments from planets might arise. Upcoming objects will challenge and polish this model, possibly uncovering developmental mechanisms absent from our solar system. The broader philosophical ramifications of research on interstellar objects reach far past astronomy, touching on core inquiries regarding how planets come to be and how widespread life might be across the cosmos. Should the variety of chemicals seen in only 3 such objects mirror the actual spectrum of planet-building conditions, the galaxy then holds an immense archive of diverse chemical formulas for crafting planets. Certain formulas could promote the rise of life forms, others could generate settings entirely inhospitable to any biological activity. The progress in technology spurred by science on interstellar objects has hastened breakthroughs across multiple disciplines. Enhanced precision in spectrometers, quicker methods for handling images, and more advanced tools for orbital calculations all stem from the rigorous needs of tracking dim, speedy objects. Such progressions will boost our skills in examining not only interstellar objects, but also the entire array of minor celestial bodies within our solar system. The global teamwork fostered by 3 Atlas offers a blueprint for tackling research hurdles that cross borders. Whenever the cosmos presents events demanding swift joint action, astronomers have shown an impressive capacity to drop competitive rivalries and prioritize common objectives in discovery. This sense of partnership will be vital as we gear up for impending interstellar meetings that could demand even briefer preparation times. The influence on education from these interstellar object finds is already altering the ways we instruct in planetary science and astrobiology. Learners exploring planet development today draw on cases from alien solar systems beyond just those in our vicinity. The range of chemicals uncovered by 3 Atlas and its forerunners supplies solid proof that planetary conditions can vary wildly from the Earth-centric cases that formerly filled educational materials. In readying for the following interstellar object, the insights gained from 3 Atlas go further than mere technical skills, including the mental structures required to make sense of truly foreign occurrences. We have realized that our conceptual frameworks, built from local solar system cases, might serve as flawed compasses for deciphering substances from distant stellar realms. The forthcoming object could upend our preconceptions in unforeseen manners. The grand viewpoint arising from research on interstellar objects proves both sobering and motivational. Our galaxy features planetary remnants that routinely traverse the divides between stars, fostering a gradual yet persistent swap of substances, linking remote planets over vast distances of empty space. 3 Atlas forms merely a single strand in this enormous interstellar network. Yet, probing it uncovers the complex designs that link our galaxy as one. The cosmos persists in dispatching these envoys from its profound reaches. Every such discovery brings tidings from distant realms of space and time that remain inaccessible by any other means. The knowledge we glean from these fleeting meetings with nomadic planets will shape our grasp of our role within the broader galaxy. As we observe the 3 Atlas probes fade from view during the solar conjunction shadow, it's not merely the departure of one interloper we're witnessing. We're gearing up for a future where these cosmic travelers are commonplace in our stargazing routine. As the voids among the stars shift from enigmatic voids to well-known expanses teeming with fragments from countless alien realms, another herald is already lurking in the vast obscurity of the universe, tracing its timeless path straight to our sun's domain. By the time it reaches us, we'll stand prepared. Thanks for joining us this evening on The Sleepy Explorer. If this voyage captivated you, remember to subscribe for more soothing escapades to lull you to sleep. Until next time, may you enjoy serene slumber. Good night, and thanks for listening.